Dear students, in this video I will solve some numerical problems depend upon the Bohr's theory of hydrogen atom. So, first problem is in accordance with Bohr's model, find quantum number. We have to determine the quantum number that characteristic the Earth's revolution around the Sun in an orbit radius of orbit is 1.5 into 10 to the power 11 meter with orbital speed velocity is 3 into 10 to the power 4 meter per second and mass of earth is given 6 into 10 to the power 24 kilogram. We know that as per Bohr's theory, angular momentum angular momentum is equal to n times of h upon 2 pi. As per Bohr theory, electron can only revolve in those type of orbit who satisfy the condition angular momentum is equal to nh upon 2 pi, or we know that angular momentum is mvr and it should be equal to nh upon 2 pi and n should be mvr into 2 pi upon h. And now we put the value n equal to m. This should be equal to 6 into 10 to the power 24 mass of earth. Velocity is 3 into 10 to the power 4 and radius 1.5 into 10 to the power 11, 1.5 into 10 to the power 11 into 2 pi is 3.14 upon Planck constant 6.6 into 10 to the power minus 34, and if we solve it, it becomes equal to 2.56 into 10 to the power 74. This is the quantum number of quantum number of this characteristic. Now we will move towards the second problem of this chapter. The ground state energy of hydrogen atom is minus 13.6 electron volt. This is the total energy, that is equal to minus 13.6 electron volt. What is the kinetic energy and potential energy of electron in this state? We know that kinetic energy of electron should be equal to half mv square, and mv square is equal to 1 upon 4 pi epsilon naught E into E upon R, or we can say that 1 upon 4 pi epsilon naught E square upon twice R. This is equation number 1. And the potential energy U, we know that is equal to minus 1 upon 4 pi epsilon naught E square upon R. This is the potential energy. We can consider it equation number 2. And total energy E, we know that should be equal to kinetic energy plus potential energy. Kinetic energy is 1 upon 4 pi epsilon naught E square upon twice R minus potential energy is 1 upon 4 pi epsilon naught E square upon R, and after solving it, it becomes minus 1 upon 4 pi epsilon naught E square upon twice R, and we can consider it equation number 3. So after comparing equation number 1, 2 and 3, we can see that the kinetic energy is equal to total energy. Kinetic energy is equal to kinetic energy, if you consider K, that should be equal to minus of total energy, and and potential energy. This is potential energy U. It is equal to total energy is minus 1 upon 4 pi epsilon naught E square upon twice R. So potential energy is equal to twice of total energy. And we have total energy 13.6 electron volt. So potential energy should be equal to twice of minus 13.6, that is equal to minus 27.2 electron volt, and kinetic energy should be equal to minus 13.6 electron volt. We can say 13.6 electron volt. So kinetic energy and potential energy in this state of electron, that is equal to kinetic energy is positive 13.6 electron volt and potential energy is negative minus 27.2 electron volt. Now we will move towards the next problem. Third problem is the ionization potential of hydrogen atom is 13.6 electron volt. So we can say that E means ionization potential, it should be minus 13.6 electron volt. Draw the energy level diagram showing 4 levels. 4 levels means we have to determine E1, and we know that ionization level depends the minus RHC upon N square, where N equal to 1 for a hydrogen atom. It means this minus 13.6 electron volt, it represents the energy of first level. And energy of second level, we can write E1 upon N square or E1 upon 2 square, means minus 13.6 upon 4, that becomes equal to minus 3.4 electron volt. And third level energy E3 is E1 upon 3 square minus 13.6 upon 9, or we can say this is minus 1.5 electron volt. And fourth level energy, it should be minus 13.6 upon 4 square, means 60, and it becomes equal to minus 0.85 electron volt. These are the 4 level energy, and we can see that the difference between E1 and E2, or E2 and E3, and E3 and E4 is continuously decreased, which we can represent, suppose this is E1, and separation between E1 and E2 is, this is E2, and separation between E2 and E3 is less than E1 and E2. We can see E2 minus E1 is, E2 is minus 3.4 minus 13.6, that should be equal to minus 3.4 plus 13.6. We can write 6 minus 4 2, 6 minus 4 2, 3 minus 3 0, 1, 10.2 electron volt. And if we determine E3 minus E2, E3 minus E2 means minus 1.5 minus 3.4. It becomes minus 1.5 plus 3.4 14 minus 5, 9, 2 minus 1, 1. 1.9 electron volt. So difference between E2 minus E1 is 10.2 electron volt, and it will be decreased when we determine the difference between E2 minus E3 minus E2. And after that E4 minus E3. E4 means minus 0.85 minus E3 minus 1.5, and it becomes minus 0.85 plus 1.5, and it becomes uh, 0.5 0.65 electron volt. Again it is decreased. So separation between E2 and E1, this is separation between E2 and E1, and in E3 level, this in E3 level it is decreased. Separation between E3 and E2 is less than E1 and E2. And in case of fourth level, this is E4, E4, this separation is less than this separation. Suppose this is 1, this is 2, and this is 3. So third difference is less than second difference, and second difference is less than first difference. So the energy level, difference of energy level is continuously decreased as the number of orders is increased. And so in first determination, we have to determine the energy of photon emitted when an electron falls from third to second. It means when electron falls from third to second. So it emit a photon h nu, that should be equal to E3 minus E2, and we have already determined E3 minus E2, that should be equal to 1.9 electron volt. So first answer, the energy of photon emitted when an electron falls from third orbit to second orbit, it should be the answer should be the 1.9 electron volt. And second, lambda of this photon, we have to determine the wavelength of the photon which is emitted during the transition of atom from third to second, that is h nu, or we can write it h, this h nu we can write it h c upon lambda, that should be equal to 1.9, or lambda equal to h c upon 1.9. This is in electron volt. And lambda equal to h, this is h is 6.6 into 10 to the power minus 34 c. This c is 3 into 10 to the power 8 upon 1.9 electron volt in joule. We can convert by multiplication of 1.6 into 10 to the power minus 19. And wavelength of the emitted photon during the transition of third to second, that should be equal to 6513 angstrom. This is the wavelength of emitted photon. And now third, we have to determine the what will be the minimum energy of a photon which can be absorbed by a hydrogen atom at ordinary temperature. And we know that at ordinary temperature, electron remain in n equal to 1 level. This is the electron, and at ordinary temperature it should be transit. It can be transit from 2 to 1. So E2 minus E1, we have to determine E2 minus E1. and E2 is minus, this is E2 minus E1, 10 point, and E2 minus E1 we have already determined 10.2 electron volt. At normal temperature, electron only can absorb energy and transit from 1 to 2, and it can emit photon during the transition of 2 to 1. So, energy of photon, energy of this transition should be equal to 10.2 electron volt at normal temperature. So, dear students, we have solved some numerical problems of this chapter, that is. So, my dear students, we have solved some problems of chapter Bohr's theory of hydrogen atom. We will do some more problems in another video. Thank you very much.